So I'm just saying.
Yep, ready.
Oh, no, I didn't have that. Basically said.
Yeah. Dr. Cobb, do you want to give a short introduction into?
Sure.
Yeah.
This is Tim.
Hey,
Tim's been working with me for, gosh, 2 years now. And in the last, for a senior project, wanted to start playing with these CUDA cards that we have available in this laboratory. And so Tim's really the high performance computing and getting the most out of the hardware. And so this seemed like a logical thing for him to try and do. And so he did work to actually benchmark the labs and just recently presented that work at the science conference in Savannah. So now we have Tim Herold presenting to us about his senior research.
Thank you. So yeah, I benchmarked, or at least attempted to benchmark, and I'm still working on benchmarking the Mercer cluster. So some of you might not know what a benchmark is, pulled from a bunch of definitions and things like that, with a little bit of my own flavor. Benchmark is the act of evaluating the relative performance of something. And specifically with computers, it's testing the performance of a computer. And there are a lot of ways to do this. There are a lot of tools out there to benchmark computers. There are a lot of tools out there to benchmark distributed computers like clusters. But there are not very many tools out there that incorporate everything together, where you can sit down and with one set of code benchmark all the aspects of whatever system you may have in front of you, be it a computer with a single core, a computer with multiple cores, multiple computers with multiple cores, CUDA, things like that. So that's what I'm attempting to do here, to incorporate everything all in one, so that you can sit down, run once, and really get a good profile of what your system's capabilities are. This was obviously tested on Mercer's cluster. Mercer cluster, for those of you that don't know, is just an aggregate of the classroom labs here. So we've got Troy, which is upstairs, lab 306, Ithaca, right here, lab 204, and Hades downstairs, lab 100. They're all tied together with a head node Zeus that's parked right next to Gopher downstairs, and that's all accessible through a message passing interface that's been installed on Zeus and all the machines here. So if you have access to Zeus, which you'll get if you take Dr. Khan's high performance computing class, you have access to these labs. You can learn to do this yourself. It's very exciting. So how did I go about taking the most general approach to benchmarking these computers? Well, I can split it up into 5 basic steps. The first step is serial code that runs on one processor. This is what you see in your 245 classes and your 204 classes, your 205 classes. This is what you usually write. It's code that executes on a single core. That's your most basic baseline, just write code and run it. Then beyond that, there's multi-threaded and multi-processing, which is a shared memory application where you have more than one CPU or a CPU with multiple cores that share the same memory block. In other words, they're on the same motherboard. A lot of times if there's multiple processors, there's also a bus in between the two that puts some data latency in there. But for the most part, it's like all of the processors are sharing the exact same memory block, even through communication. Above that, there's GPU, General Purpose Computing on Graphics Processing Units. This is what CUDA is. So in this lab specifically, we have NVIDIA GT330 video cards. CUDA, developed by NVIDIA, is a set of libraries that allow you to write numerical code to run on video cards. So you're using a graphics processing unit, which is very, very dense in terms of cores. These GPUs, as small as they are, have 96 cores on them. So it's like having 96 CPUs in a sense. The architecture is a little bit different. There's not a lot of memory. There's only 1 gig of memory on each card. But there's very, very high bandwidth. So even though you can't store a lot of data, you can move that data around very fast. Also, these processors are set up as stream processors, which means instead of constantly executing the same command on one core, you can push a set of commands across all of the cores. Kind of like vector processing, but not. So that kind of takes care of each individual computer. But since we're working on a cluster, we also want to see how the cluster as a whole performs. So we switched to multi-node, which is a completely new memory paradigm. You have distributed memory now. The memory, instead of being all located in one place, is now shared amongst all the machines. Each machine has its own memory. So we need to split up our data and rework our algorithm to be able to be pulled apart and processed in small chunks that aren't connected. Once we've done that, we test hybrid multi-node, which after we've distributed all the memory, we now have a shared memory environment on each machine. So we distribute our memory out to each machine. Each machine now has multiple CPUs and multiple cores. So we divvy that memory that's already been shared again and run multi-threaded on each machine. All right, so starting with serial code. I choose to use dense matrix multiplication. Why? One, because it's relatively simple. Two, because it's not extremely data dependent, but there is a lot of data. And three, because, quite frankly, it's slow. It's an n-cubed algorithm, which means that for small data sets, yes, it runs very fast, but it gets very slow very fast. So it also gave me a chance to learn how to pass data around effectively, because even though each set of machines does not need to have all of the data, each machine does have to have its specific set of data set up properly. And you can split this algorithm up. You can see, I know a lot of you already know how to multiply matrices, but to find the cell of a resultant matrix, you take a row and multiply by a column. It ends up in a triply nested for loop, hence so once we've done that relatively simple test, it was time to go ahead and break up the code. It's a relatively simple process, but the difficulty is for strange dimension sizes. You get different chunks. So what I'm doing is I'm taking a square matrix and trying to divide it evenly amongst however many computers I get the process to work with. So you can see here, looks like they have 3 tasks or 3 computers. They're splitting their matrix up into 3 chunks and then telling each process to do its own particular chunk. It's relatively simple. You split it up as evenly as you can, and then for whatever's left over, you just keep applying another row to each computer until it's split as evenly as possible. The difference between any 2 computers is at most 1 row. So we've figured out kind of how to split up our data. We can go ahead and do shared memory. I talked to you about this. To do this, I used OpenMP, which is the open source multiprocessing libraries. OpenMP allows you to put statements into your code that will designate to the operating system that this code should be run in parallel. OpenMP takes care of most of the work for you in the sense that it figures out how to split it up among the processors, how to schedule it. You can specify to OpenMP how you want to schedule it. Scheduling is a very big topic with this. I use dynamic scheduling, which means that whenever there's a core available, it's going to try and process something. There are other ways to do it. You can do it in static chunks, where you say each processor is going to calculate 10 calculations and then grab another chunk. That's not how I chose to do it, because the most efficient use of resources is generally going to be different for different machines. So a dynamic seemed to work best across different systems. Once you've looked at shared memory, I started to look at CUDA. And the way that I approach CUDA is not so much trying to use the CPU and the GPU together, but rather the CPU sets up the problem, sends it to the GPU, which does the work, and then sends the result back. There's a lot to CUDA. It's a completely different architecture. It's something that most of you here have never seen before. But conceptually thinking, it's like having all of these labs times 30 in one little card. And so there are different ways that you can manage your memory. You kind of have to think of memory in terms of 3D space, where you end up with this cube of data and you're taking slices off of it, pushing down on top of the cores instead of sliding data across. And so algorithms change. It's still an n-cubed algorithm. It's still a regular matrix multiplication. But essentially what you're doing is you're telling each kernel what they're going to do, or each processor what they're going to do, as a reduction rather than a full n-cubed algorithm, I guess. but it's very fast. So, having run all the tests for a single machine, came up with some values and kind of saw where the machines were at. Down here, where is my cursor? There it is. So the red line here is serial code. This is on a log plot because CUDA was so fast. You know, this is your baseline. This is your standard performance single thread. Just kind of crunch it down. We split into OpenMP with the green line here. You can see you do get a performance boost. If you were looking at this in a regular plot, it would look something like this. It's not. All right, so if this is OpenMP, this is going to be your serial code. The gap widens as the data sets get larger, but it's not a perfect increase in efficiency. There's a law called the Amdahl's law that tells us that every time you add a processor, you don't necessarily get 100% more performance. And this demonstrates that. The blue line that you see is CUDA
If we go back
performance.
to the red and green, why is there a dip?
Why is there a dip? That's a good question. This is something that we're still trying to work on.
Okay.
These points here are the size of my data set. You can see down here. And it just so happens that these two low data sets are powers of 2 that completely confuse the machines in here. And we're not quite sure why yet. It's some sort of, I think it has to do with the way it caches the data on the CPU. It achieves the right answer. If you sum the diagonal matrix, it's the same as it would be for a serial code or the matrix is solved correctly. But for some reason, it takes much, much, much longer if the dimension is a power of 2, specifically 10, 24, and 2048.
Have you tried 1,000?
I have tried 1,000 and it works just fine.
Oh.
And I've tried 2,500 and it works just fine. These are the results that I had when I ran my long tests. So I put those in here, but we're still trying to figure out exactly why it's doing that. But it's something useful to know. And then the blue line there is CUDA, and as you can see, CUDA outperforms an individual computer tremendously, comparative more to the cluster than it is to an individual machine. But you can see at the beginning for small data sets, it's actually a little bit slower just because of the overhead of structuring your data and moving your data to the video card. So now that the single machine has been tested, we're splitting to multiple nodes. How do we do this? There's libraries for the message passing interface, the open source message passing interface, which allows a computer to communicate to another computer over a network. And so in your code, you can send data, receive data, restructure data. And each computer now, because it's distributed memory, has its own data space. So the way I've split it up is that there is one node on each process whose job is strictly to handle data. It does not do computation. All subsequent machines do the computation. So that primary machine sets up the data, fills the matrices, prepares them to be sent to each machine. Each machine gets the entire matrix B and its portion of matrix A, which is then stored in memory that it allocates. So each computer is allocating its own memory space, and then filling it with data that it receives from the head node. And then once it's done computing, it sends it back. So the first stage of this is just regular distributed memory. This is essentially serial computation, but done on multiple machines. So each machine uses its chunk, calculates using only one processor, and returns. After that, we've split into hybrid memory. So once the data has been sent out, each machine manages its own memory, puts its chunk into memory, and then OpenMP takes over, and with that shared memory space, runs multiple threads on each machine. So you're running multiple machines, running multiple threads, and multiple processors each. Results from that, I don't know how well you can see that, it doesn't look very good on my screen.